And now that we've talked a little bit about what a mole is and how to go about weighing out a mole of either an element or a compound, I want to look a little bit about mole relationships in laboratory measurement. So there are three mole relationships, and the first one is just the definition of a mole. 1 mole of any substance is equal to 6.02 times 10 to the 23rd representative particles. Those particles could be atoms or ions or molecules or formula units or donuts or chickens or spaceships. It doesn't matter what it is that you're counting. 1 mole is equal to 6.02 times 10 to the 23rd. Now normally we're only counting out submicroscopic particles, because 6.02 times 10 to the 23rd of anything that you could see would generate its own gravity well. So that's the first mole relationship, is the particle to mole relationship. The second one uses atomic masses off the periodic table. We know that the atomic mass, or the relative atomic mass on the periodic table in grams, is the molar mass, and that is 1 mole of a substance. So if you have the molar mass, you know how much 6.02 times 10 to the 23rd of that particular particle weighs. The third relationship is the volume to mass relationship, which only applies to gases. And essentially what's going on here is, if you know the temperature and pressure of a confined gas, you can infer from that information how many particles are in the container. And so standard temperature and pressure is a specific value that is kind of universally agreed upon that gas phase relationships are going to be measured at, and it's 1 atmosphere and 0 degrees Celsius. So at standard temperature and pressure, 1 mole of any gas will fill a volume of 22.4 liters. And we generally take these relationships and we put them together in what I like to call the mole map. So this is the relationship between all of the conversions and 1 mole. So if you have 1 mole of a substance, we can do a number of conversions that can get us to these other values. And why are these important? Well, chemical processes, laboratory practices, the things that we measure about things, or the processes that we observe, I should say, all happen at the particle level. Or if we scale up, we might say the molar level, right? It's particles interacting, colliding with one another, rearranging their bonds, sharing electrons, transferring electrons. Between particular particles is where chemistry happens. But those particles are too small and there's too many of them to ever directly track. And so when we are doing lab work, laboratory measurements primarily happen here at the mass or the volume level. And so if we know those things, if we can make those measurements in the lab, we can then convert those measurements into either moles or particles. Then we can figure out what's going on in any particular chemical process. All right, so let's go through each of these one at a time. We're going to start with the mass to mole relationship and how we're going to use these. And again, chemical reactions happen at the mole and particle level, but moles cannot be directly measured or observed. So typically we're going to go about measuring things using masses or volumes. And so here's how that might go. If you were going to do a reaction with magnesium carbonate, how many moles or how many particles would you be reacting if you had 33.7 grams of magnesium carbonate? The first thing you're going to need to sort out here is, what is the molar mass of magnesium carbonate? Is 33.71 more or less than a mole of that substance? So you're going to first need a chemical formula, and then you're going to need a molar mass. So you should go about doing that. Pause the video, find a chemical formula, add up the molar masses. Don't forget, we're going to round this to 2 decimal places when we pull those numbers off the periodic table. Go ahead and pause it. Okay, so hopefully you did that, and you got magnesium carbonate, MgCO3, carbonate CO3 2 minus, magnesium ion is 2 plus. It'll take 1 of each. You can add all those up. You should get 84.32 grams. Remember, if you're within 1 or 2 of my last digit, the last digit is estimated anyway. So if we look at this, again, you ask the question, do we have more or less than a mole? And we certainly have less than 1 mole of magnesium carbonate. If we want to take the grams of magnesium carbonate and convert it to moles, we're going to need to set up a conversion table. So set up your game board. was a while back, so you got to think about this. Where does the game start? The game starts in the top left corner. That's where we're going to put our given piece of information. It's going to be really important that you practice writing both units and compounds in these conversions, because eventually we're going to set up chemical equations and we're going to convert from one substance to another substance. So you don't only need the grams, but you need to know that it's grams of magnesium carbonate, and you need to get into that practice. Okay, our mass to mole relationship is that 1 mole of any substance is equal to its molar mass. Well, we have our molar mass there. We want grams to go on bottom because we want the grams to cancel, which means we want moles on top. Every mole conversion on the mole map is 1 mole equals something. In this case, 1 mole is equal to 84.32 grams of magnesium carbonate. The grams of magnesium carbonate are going to cancel. You're going to multiply across the top, divide across the bottom, and think about sig digs, think about units. Go ahead and pause the video, do the calculation, write down your answer. And so if you did that, we have 4 sig digs in both of our numbers, so we'd expect 4 sig digs in the answer, 0.3998 moles of magnesium carbonate. And again, you want to think about this one as well in terms of, does that number make sense? Well, it takes 84 grams to make a mole of magnesium carbonate. 33 is less than half. So you expect less than 0.5 moles, and sure enough, that's what we have in front of us. All right, let's look at the next one. So the volume to mole relationship. The volume to mole relationship comes from Avogadro's hypothesis. Remember that the number of particles in a mole is sometimes referred to as Avogadro's number because we were able to determine that number through a theoretical framework provided by Avogadro, who said, equal volumes of gases at the same temperature and pressure contain equal numbers of particles. We'll come back to this when we talk about gases later in this class. The short version goes like this. Temperature is a measure of how fast particles are moving, and pressure is a measure of how often the particles in a gas container collide with the surface of the container. And so if you have equal volumes of gases, so 2 containers that are the same size, and they are at the same temperature, means the particles are moving at the same speed, and they have the same pressure, meaning you get the same number of particle collisions with the wall per unit time, then you have to have the same number of particles in those 2 containers. If you had more particles in one container than the other, but the particles were moving the same speed and the containers were the same size, you would get more collisions and hence a higher pressure. So by measuring temperature, pressure, and volume, which are all measurable properties, we can infer how many particles are in a container, even though they can never be counted because there are too many of them. And what we find is that at standard temperature and pressure, 0 degrees Celsius, or 273 Kelvin, and 1 atmosphere of pressure, that any gas will fill a container that is 22.4 liters. Okay, so if we ask the question, how many moles are contained in 3.21 liters of carbon monoxide gas at STP? Again, we're going to set up our game board. Now, we're not doing a mass conversion, so you don't need a molar mass here. You do need to know you're at standard temperature and pressure. If we didn't have the at standard temperature and pressure here, you could simply shrug your shoulders and say, I don't know how many moles are contained in that because I need a temperature and pressure before I can make that decision. We give our given piece of information in the top left corner. Make sure you have units and compound. Again, every mole conversion is 1 mole of something equals. So this time it's 1 mole of CO equals 22.4 liters of CO. Again, it doesn't matter what the gas is. If you're at standard temperature and pressure, every gas has a molar volume of 22.4 liters. All right, so liters of CO are going to cancel. You're going to multiply across the top, divide across the bottom, and we end up with 1.43 moles of CO. Let's look at our last conversion. So this is the representative particles to mole relationship. How many molecules are there in 2.31 moles of PCl5? Name of that compound, of course, is going to be phosphorus pentachloride. And so again, we're going to set up our game board, put our given piece of information in the top right corner. Again, every mole conversion is 1 mole of something equals. This time, since we're going from moles to molecules, We want those moles to be on the bottom so that they cancel out. There are 6.02 times 10 to the 23rd molecules of PCl5. And so we're going to cancel out moles. We're going to multiply across the top. And you should get 1.39 times 10 to the 24th molecules of PCl5. Now what if I asked you how many atoms were in 2.31 moles of PCl5? Well, first I need to know how many molecules I have. So we're going to set up the same game board, the same conversion that we just did, but now we need another step. How many atoms are there per molecule? So you have 5 chlorines and 1 phosphorus, so that's going to be 6 atoms per molecule of PCl5. And now your molecules here are going to cancel. So you're going to multiply across the top, 2.31 times 6.02 times 10 to the 23rd times 6. And that's going to get you 8.34 times 10 to the 24th atoms. What if I had changed the question one more time and said how many formula units are in 2.31 molecules of PCl5? Well, we don't need a game board for that because PCl5 is a covalent compound. There are no formula units, and you could simply respond 0 without doing any math there. And that's an issue of understanding technical terminology. So 3 conversions, mole to mass, mole to volume of a gas at STP, mole to representative particles. Those are our mole conversions.